Hello everyone and welcome back to our PML School. Today we have our 10th session out of 20, so after this session we will have half term. But not for long. I mean, we are planning our next session in 2 weeks' time as usual. So today, as you see on the slide here, I'm going to present how to develop a turnover model for an endogenous compound in Phoenix Bin Lin. And as with all sessions of the PML School, we have taken an example from the Gabrielsson and Dr. book. So this is exercise PK32 from that book, turnover 3, nonlinear disposition. And as usual, after this session, we will make available the textual model as well as the slide deck. We will record this session and post the link to the recording together with the other materials on the Certara forum after the event. During the session, if you have some comments or questions, please post them into the Q&A panel right to the WebEx console. We will get to this Q&A after the presentation. Oops, switch. Okay, so our example today is a study of an endogenous compound. We will analyze multiple intravenous infusion data with nonlinear disposition, and we want to find estimates for a number of PK parameters. Since we will be dealing with saturated elimination, we have the two parameters from the Michaelis-Menten equation here, Vmax, the maximum metabolic capacity, as well as Km, the Michaelis-Menten constant. And in addition to that, the V, the volume of distribution, Kn, the rate of synthesis of this endogenous compound, as well as plasma clearance, Cl. So here's a problem specification. In order to study the pharmacokinetics of this endogenous compound, a volunteer was given multiple intravenous bolus and infusion doses of this compound, as summarized in this table. As you can see, this is a highly variable dosing scheme with several bolus followed by infusion doses. And plasma concentrations were sampled over 450 minutes. So we start with exploratory analysis. So here is the concentration over the 450 minutes. In the first section, you see it starts at a high concentration due to the IV bolus given at the beginning. But then you see this is actually the first decline part of the curve. This is actually the infusion time, but you see it's still eliminated much faster than the infusion adds compound to the central compartment. After this infusion is complete, the elimination goes on until the same pattern repeats itself here in the middle part of the curve. But then for the last part, there's some higher concentration, and here you see this is the first bolus, the IV bolus, followed by the infusion part. And here in the infusion part, you really see that we are have capacity limitations of the metabolism, and you see an increase of the concentration, followed then after at the end of the infusion by a steep decline with the elimination of the compound. So this is what we want to analyze, and for this, we want to develop a turnover model. And the endogenous compound is hyaluronan, or short HA. And it is synthesized in the body by a zero-order turnover rate Kn. This is the input for the central compartment. But we also have an additional input. This is the infusion, INF, that gets into the central compartment. And the loss of or elimination of the compound is being modeled by a Michaelis-Menten elimination with parameters Vmax and Km. So there is a more detailed information about the study and the compound in the Gabrielsson and Dr book. So if you have any more further or detailed questions about it, I would refer you to the book. Let's move on. So how do we build the turnover model? As usual, we start from the built-in options. Make sure that you uncheck the population box because we only have one profile. We stick with the type of a PK model. For the parameterization, we'll let the default clearance parameterization, and we are checking on the box saturating. This means the clearance is saturated. And this will switch, as you see here on the right-hand side, to the Michaelis-Menten type of elimination. Absorption, it stays with intravenous, and we only have one compartment. We also need to switch on this box, infusion possible, since it's an infusion dose. And the final thing we need to set in the built-in options is changing from the additive residual error model to a multiplicative. And then we're there. From this status on, we switch to the graphical model, and this is and then it appears this kind of picture of the model. It's a one compartment system where we measure the concentration in the central compartment, and we have a saturated elimination, as you see here. We don't need to do any modifications on the graphical model, so we switch directly to the textual model. And this is what you get direct from these built-in options. This is the textual code that we get from the built-in options. And there's not very much that we need to add to modify to get to the final model. So we need to add the synthesis of the endogenous compound. This is not yet modeled into the code. Let's move on. Just for your reference, these are the model equations, and below that the textual model, and you see in yellow the additions that we have to make to the code. So we start with just with a linear model. This is it. So the change in concentrations equals the input, infusion, plus the synthesis. This is the synthesis of the endogenous compound, and with a linear elimination, it looks like minus clearance times concentration. This is a first-order elimination. But for a saturated clearance, the clearance is expressed with a Michaelis-Menten equation, Vmax over Km plus C, and that is then taken, this part is then exchanged with this one. So you get, this is our final model, the equation of the turnover model. And this is what you can see here in the first line. Okay, so we are introducing the synthesis of the endogenous compound just by the zero order rate constant, Kn. We have to add this as a structure parameter, and so we say Kn is a typical value of Kn. And then at the end, we also provide a fixed effect where we give the lower bound initial estimates and upper bound. And as usual, we don't use boundaries at all for initial estimates. We just give an initial estimate value. So this is a textual model. One word maybe about dosing. As we've seen in one of the previous slides, we have a highly variable dosing regimen for this study, and you might wonder how Phoenix is handling this. And just for your information, dosing is being handled outside the model code. This might be different with other modeling packages, but Phoenix is handling the dosing separately. So the only thing in the model code is to specify the dosing point, which is the second line, dose point A1. And I will show you during the software demonstration how to enter the variable dosing scheme. Okay, now for the fitting, we would need some initial estimates. And these we typically get from an NCA analysis. Clearance is dose over AUC, and in this case, it's about 0.35 liters per minute. Volume of distribution is dose over C0, and this is about 5 liters. Kn is a baseline concentration times clearance, and is about 7. Sorry, this is a typo. C actually means Cl, not C. All right, and it's about 7. Vmax and Km cannot be easily estimated from this from the NCA or so. But as we've seen in the plot, the elimination during the first infusions were higher than the infusion rate, so values should be beyond 100. And here we will use the initial estimates tool in Phoenix to get good starting values. So in this example, we will show you how to incorporate secondary parameters. Secondary parameters are derived from primary PK parameters. So we've got here some equations on the left-hand side. For example, the intrinsic clearance is expressed with Vmax over Km. And this is how you put them into the textual code. You just use a secondary statement where you just input the equation directly into the code, like you see here. The same for the terminal half-life, which is ln2 times V times Km over Vmax. K out is Vmax times V over Km. And the mean residence times is 1 over K out. So this is just easily entered at the bottom of the code at the later part. And these will be calculated with the fitting. So with that, I think we are at the demo. Yeah, we can show the demo. So let me share my application, Phoenix. So, Chris, can you see the screen? Okay.
Yes, it looks good, Bernd.
Okay, all right. So here is the data that we have. So we've got 2 columns, time and the plasma concentration. And here is the dosing table as you've seen in the slide. So you got the dose point, A1, and the dose ID, and I come to that, why we will need this. We got a start time for the infusion and an end time for the infusion, an amount and a combined amount. The combined amount is the one from the bolus, bolus dose plus infusion dose. So for the Phoenix model, if you want to use this dosing table, we need 1 out of 2 additional information that we can generate from this dosing table, and that is the duration, which is just end time minus the start time, and the rate, which is just the amount divided by the duration. And this is we can typically do through a data wizard object. So I send this dosing sheet to a data wizard object where I have to specify an action. In this case, I would like to do a transformation. So I'd say add. And as a arithmetic type of transformation, I want to have x minus y. Oops, that's the wrong one, x minus y. And I say this is the duration. So I need to specify x and y here as well. So x is end time and y is start time. If we do this, you see here the duration is then measured here. All 3 infusions roughly half an hour, so 30 minutes. That's good. But now we need to calculate the rate. So I need to add another transformation and say this is x by y. Say this is the rate. Oops. Go back to setup and say x is the amount and y is the duration. If you do that, you are here. So these are the individual rates. So this is the final dosing table that we can use not only for the Phoenix model, but also for the NCA analysis that we will need to get to some initial estimates. To get to some additional estimates, I mean, if you want to run NCA analysis on a multiple dose profile, you need to specify a dose ID. So for each dose, this has to be indicated by an index. And this is why I have inserted here a dose ID in the dosing table, but I need to add this to the PK data as well. So I need to send this to a data wizard object. And again, here I need a transformation. In this case, since I know roughly the dosing times, infusion times, I can do it with a custom transformation time and say, this is a dose ID. And I said, if, just an if statement, if time less than 125, this was the first profile, I want to have a dose ID of 1. But if time less than 260, this was a second profile, it's 2. Otherwise, it's 3. So with this simple if statement, you can introduce a oops. I need another parenthesis. I could introduce this dose ID, which you see here, 1, 2, 3. And now I can send this directly to a NCA object, where I need to sort by the dose ID in order to get analysis for each profile. Time is already matched, and I need CP for concentration. For dosing, I'll take this dosing table here. Okay, and I also sort by dose. I need to change this to IV infusion and say this is dose is the amount and duration is the length and time of dose is start of time. And then you can execute. Wait a second, what was that? Profile dose ID 1. There's a problem with dose ID 1. This doesn't work. Okay, I need the combined amount. Yeah, that's the one. I need the combined amount here, not just this one. And execute. And this is the final parameters for each dose ID. So what we are interested in is the, wait a second, volume and clearance. So these would be the initial estimates for that. Okay, now the next thing is to model the data. So in this case, we don't need the dose ID. We just can take this one and send this to an original sheet to a Phoenix model. And as we said, we uncheck the population box. We check the saturating checkbox, intravenous 1, number of compartments 1, and now we just, infusion is possible. This is for the infusion part, and then we need to change from additive to multiplicative model. And that's all we need. So we can deal with the mapping. So main is time and CP is the ops. And for the dosing, we take this dosing sheet and set the amount is A1, start time is time, and A1 rate is rate. And maybe one thing you should notice, this is Phoenix 7.0, and we have added a new checkbox here for duration. If you have infusions, you can now specify either the length of infusions, the duration, or the rate. So if I would switch this on to duration, I could also use the duration instead of the rate. Okay, but now this is all fine. We can switch first to maybe to graphical, but you see this is a picture that we had. So we go further and edit as textual. This is a code. And here you just need to specify the synthesis of the endogenous compound. And that is, I just introduce this here with K-in. Since I've introduced this here, it says variable kin undefined. Okay, so we need to add this as a structural parameter, stparm. equals TVKN, right? So now the typical value is not specified, so we can say fix f TVKN equals no boundaries. We just give it a 1. And that's it. So in this status, I mean, we can now start to fit the model. But as I said, I mean, we can also specify some secondary parameters. Like, I'll just say, for example, secondary CL0 equals Vmax over Km. This is 1. Vmax comes with a capital M, sorry. Vmax over Km. Now the secondary, we can say T half, and that equals ln of 2 times V times divided by Vmax over Km. Okay. And we've got another secondary parameter like K out. That equals to Vmax over Km over V. And finally, we can specify the mean residence time or turnover time with 1 over K out. And that's it. Okay. So this is a final textual model, which will take care of this profile. Let's go to the initial estimate step. Okay, so here we have a start time and the duration. The last measurement was at 450, so let's see. Need to go up to 500, and you see here some accumulation takes place. So we said we had a volume of 15 and a Kn of 7. That's what we said. Now we need to take care of the Vmax and Km parameter, and we said it must be bigger than maybe 100. Again, it's very slow. So let's see. No, that's too much. It requires a little bit of patience to get to better values. But in this case, you see that there's no option to copy or paste, move these initial estimates to the textual code. So there's a disconnect. So what I would need to do is to enter these initial estimates into the textual code. But for this exercise, even starting with 1, the solution is very trivial. So I can run this model without entering the proper initial estimate. So let's just fit the model. And you see, this is a fit. Let's just widen the graph a little bit. 6.0. So you see, it's a very nice fit over here. And let's look at some diagnostics like the predicted actual plot. Very nice spread of the data. Here's also a picture. This is something we just see for multiple dose profile. The predicted and actual values, observed values after dose. So these are now on top of each other or on the lattice, if you want. And then we've got the individual weighted residuals versus time. You see here, very nice and clean. All, the blue line is very close to the x-axis, and same with the residuals versus the predicted concentration. It's also nice, and whatever. And then we've got the QQ plot. It also shows a nice outcome. So this is the fit, and you see how it can be done with this very simple modification of the code derived from the built-in options. Maybe at this point in time we could check whether a linear elimination model would come up with a similar kind of result, or if you really need saturated elimination. So for this, we just send this to a Phoenix model once again, and we should properly name our objects now. So to create it, and here we call this model linear. Okay, and what we need to do here is just say infusion is possible, no saturating. We also switch to the multiplicative model, uncheck population, use the dosing once again. So we have the start time is time, A1 is amount, and rate is, rate is rate. So with this, I can now go directly to the textual model and say this is Kn minus Cl times C. And to shortcut, I just specify this as a fixed effect. Okay. And just fit the model. So this is a plot now. Let's also widen this. You see this plot is a little bit worse, you see. And if you can see it maybe better here, where you see in the lower concentration range, it's over-predicting, and in the upper concentration range, it's under-predicting the actual values. So this should be worse. But let's have a look at the overall. We have a minus 2LL of 644, ICAIC is 652, and Bayesian information criterion of 661. Let's just pop it out of the model object and compare it with the overall of the saturated model. And now look at this side by side. You see, okay, the saturated one is obviously much better, so a significant improvement in all those diagnostic values. So that shows that the saturated model is the appropriate one. Okay, with this, I want to switch back to the slides. And so go back to the slides again. So let's move on. So again, here the results. This is a fit from the saturated model with saturated elimination. And you see here are the parameter estimates that we see with standard errors, and the CV% looks pretty good, pretty sharp estimates. with CV% between 3 and 11. So this is really a nice fit, nice outcome. And with this, I am at the end of the presentation, just summarizing the presentation. So we developed a turnover model, and where we set up multiple intravenous infusions for multiple dose profile. And we did obtain some initial estimates and derived some secondary parameters, and finally fitted the model, examined the results, and compared the results with a simple linear model, and we concluded that the saturated elimination model is the best model of the two. With that, I'm at the end of my presentation. I think the next thing is Q&A session, so I'll hand over to Chris. Chris, your turn.
Thanks, Bernd. We have a few questions coming in. If some of you have some questions here, please use the Q&A panel in the WebEx to submit your questions. We will address some in this session here as well as on the Certara forum. So Bernd, the first question, when you were doing the NCA, can you talk a little bit more about the combined, is this a combined dose of both the bolus and infusion, and why would that be done?
Okay, yes, it's a combined amount. So if you go back to the NCA object, yeah. So what I did did specify in the dosing table 3 dose IDs, where I just said, I mean, these were 2 different infusion rates, if you will, from the first one plus the second one. But it's only important for the second one how long it runs with the second one. But the dose amount itself is the combined amount, both of these dose options. And this is then being executed here with the NCA, and you get all the parameters, especially those normalized ones with reference to the actual dose, because it's a combined dose, bolus as well as infusion. Chris?
Okay, thank you for that. Next question, can you talk a little bit in the Phoenix model object about some of the dose variables, like the I-dose variable, inf rate variable, and the inf dose variable?
These are actually in the code. This is a standard. I mean, whenever you start from a Phoenix model, it will take care of a lot of optional parameters that you can set, but these are not actually required. So in case you want to make use of that, you can do that, for example. But in our instance, since we have put everything into our dosing table, we don't need the inf rate. This would be a constant for the rate of infusion. We don't need the infusion dose, because we provide that with a dosing table, and also not the dose. So these are just parameters or options of this dose point statement that are built in. And you may use it with a textual code, but what is maybe better for this highly variable dosing scheme is just use a dosing table like this, where you can specify it from a worksheet input.
Okay, so for example, you could maybe use those dose variables in a secondary parameter equation, which leads to the next question. Maybe can we take a look in a little bit more in detail on the secondary parameters that you set up, and where do they appear in the output?
Oh yes, that's right. I didn't show it in the output. Yeah, secondary parameters, as you see, they are all derived from primary parameters that are estimated by the program. But if you go to results, there's a specific sheet, secondary, which gives you all the secondary parameters, and here are the estimates for this.
Okay. There was one other question about the error model used was multiplicative. Can you just comment about that?
Yeah, this is something that I obviously I've got from Gabrielsson and Wendt book. So you typically start with an additive error model, so uniform weighting if you want. But if you see that some pattern in the residuals, like a fanning pattern, you want to change to a different residual error model. In this case, you see, for example, the trend curves for the residuals across the predicted concentration range are all more or less parallel to the x-axis, which should be, so that you don't see a kind of fanning pattern. But if you would see that, I mean, you can change your residual error model to see if this can fix this pattern, and you get a nice spread of your residuals across the predicted concentration range.
Okay, thanks, Bernd. I think we've covered the questions for now, and so thank you very much for that presentation. And just as a reminder, if there are follow-up questions, these can be submitted and answered on the Certara forum.
Okay. Yeah, thanks, Chris. And just before we end, I just want to show you our next event will be on March 16th, and Dan Weiner will present an analysis and a comparison of a link, turnover, and a receptor binding model. So with that, I would like to close this session. Thank you all for your continued interest, and I'll look forward to seeing you in 2 weeks' time. Thanks, and you may disconnect now.